Going live. So welcome everyone again to today's lecture, the second one on open world lifelong learning. For those of you who have not been here the first time, it's every Tuesday from 5:30 to 7:30 CEST. The link is on this slide right now. It's live streamed on YouTube, and the materials like PDFs are on the homepage displayed on this slide. A little change from last time because I'm trying to keep this interactive. I have in fact lowered down the latency, so if you're participating through YouTube, you can use the live chat now with a lot less delay than before, which will hopefully make everything more convenient. And with that said, let's dive in right into the content. So last time we essentially had an overview over the course where we talked about the challenges of continual learning, all the aspects of continual/lifelong learning, and the elements that we are going to consider throughout the course. So this week we're going to start with a very particular one, which is basically going to be knowledge transfer. So we're going to talk about things such as transfer learning, domain adaptation, and then eventually revolve back to continual lifelong machine learning with a couple of intermediate steps. So starting out, we have not actually had a definition of lifelong learning in the first lecture. So let me try to give you one of the ones that are more popular, just to have something to talk about. This one is by Thrun from 1996. The system has performed n tasks. When faced with the n plus 1th task, it uses the knowledge gained from the n tasks to help the n plus 1th task. So as we can see, it's not a very comprehensive definition, and it focuses on one aspect quite in particular, which is when faced with an n plus 1th task, it uses the knowledge gained from the previous ones. So it's very focused on just the idea that we can use whatever knowledge we have gathered to advance a new task. So in that sense, let me already ask you the first question for today, which is going to be, what do you think is knowledge in a machine learning system? So knowledge maybe in a wide sense. And as I've just said, you can answer through the Teams or you can answer on YouTube.
I think something like the awareness of similarity or something like that.
The awareness of similarity. Okay. So the awareness of similarity then following this definition of between the n and the n plus 1 task, or the awareness between similarity of the data points that we have, maybe? Let's go with the latter one. Let's go with an awareness of, let's call it correlations, right? The correlations in the data, which is a good idea. Now, the question is, of course, how do we express such similarities, such correlations? Someone on YouTube is correctly now saying the learned pattern, the learned parameters, and someone else is saying the learned patterns. And I think for most machine learning systems, when you ask people what they refer to when they talk about knowledge, they'll tell you something about parameters, about patterns, someone saying the reduction of uncertainty. But now someone's also actually writing a message that in the machine learning sense, parameters are considered as knowledge, but maybe this is not capturing the full meaning of knowledge. And I very much agree with that. So let's talk about this for a second at the hand of one popular example of an actual continual/lifelong learning system. And this one's called Never Ending Language Learner, or NEL for short, where we can just briefly discuss where knowledge is a lot more than just parameters. As a small note, the system is displayed on the bottom left of this slide. We're not going to talk about it in extreme detail today because it's quite frankly just too early to talk about it in lecture 2, but we will revisit it later again throughout the course. For now, let's just go with the idea that NEL has something that's called a knowledge base, and in that knowledge base, there are beliefs. So NEL ran 24/7 for around 8 years actually, and over this time it has accumulated 50 million of such beliefs by reading the web. And what these beliefs are, they're actually stored in a so-called relational database where belief is something like sport uses equipment and then the pair of soccer and balls, or just also stored facts like barley is a grain. So in that sense, it's not the same thing as parameters in some machine learning model, but it's really here facts and relationships, which is also one form of knowledge. And quite similarly, there was a, let's say, complementary system that was called never-ending image learner, which again works on a sort of similar, based on a similar idea, where you now also have detectors, for example, for images, where you can extract objects like monitors and keyboards and so on. But you still have this notion that there's an additional form of knowledge on top in form of this relational discovery to learn facts such that a monitor is a part of a desktop computer, or that television looks similar to a monitor. I mean, maybe that's something that someone just referred to about the similarities. So that's also one form of knowledge. But quite crucially now, when we look back at this definition, we can figure out some other parts that are maybe missing apart from the question about what is knowledge. It's also the question of what is a task. It's also a question of is data accumulated, is data stored, and more precisely, because this is the central part of this specific definition, what are the ways to help the n+1 task? So this, what does help in this case actually mean? And so something that has maybe captured the essence of this idea of help the n+1 task is this notion of transfer learning. So we have this assumption that we already have some knowledge in whatever form this exists on an initial set of tasks. And now based on this initial set of knowledge, we can transfer to a target task. So on the top left, you can see this by basically a learning system being comprised of multiple tasks from before, but then eventually having this set of source tasks in some form of knowledge, whether this is parameters or a knowledge base or something else, being helpful towards the target task. On the right, top right, you'll see some maybe more intuitive examples of this. So we could think of about something like if we learn to play the violin, then the knowledge that we have learned should maybe more or less obviously help transfer to the piano so that we can learn the piano. Whether this is actually true or not is a different question, but I would say the general assumption is that if you, or the general consensus is that if you trained to learn the violin and some other music instruments, the more music instruments you learn, the easier it maybe gets for you. And with that, let's maybe think about what are the types of shifts that we can think of. So you specifically, when you think of now of this knowledge transfer, what are the types of shifts that can occur in practice where we need to basically transfer this knowledge, or maybe where we also don't need to transfer knowledge, but something shifts independently. Okay, so someone saying label shift, that's quite a good idea. So we'll take a look at that in a second. What about some other shifts? So label shift, I suppose, refers to in the supervised setting where we want to label concepts, and then these labels can eventually change. What about other things that are not label shift? Concept shift. So someone's saying concept shift. Okay, I would
Danger.
danger, you say. So the danger shifts. Can you elaborate on that, or do you want to write something more
Like
about that?
a car that we can identify which situations are dangerous or which are not, or when a human could be in danger to get harmed, something like that. That could be identified.
Right.
I'm not sure.
Correct. Maybe let's formulate it in a slightly different way, and maybe let's formulate it in the way that it has been formulated in the literature. So maybe not surprisingly, there's an entire book that is called Dataset Shift in Machine Learning, which you might want to take a look at, where all these sorts of different ways in which data can shift, in which tasks can shift, is elaborated on. But the consensus would be that there are these, let's say, these major three types of shifts here illustrated on the slide. And so the first one, sticking away a little bit from the buzzwords behind it or from the names behind it, is really the idea that our data distribution changes. So you can see it in the first panel of the left besides the no data shift, where although maybe the two colors of blue and yellow stay the same, the covariates in this case shift, so the distribution changes, but the task itself and maybe the decision boundary that you draw here does not necessarily so much change, or maybe it could. The second one someone's already mentioned is the label shift, which would be the distribution of your labels changes. And the third one someone's also already mentioned is the concept shift, where maybe the prediction of a label given the data distribution changes, so that the decision boundary that we need to draw overall is completely different from before. And so with that, we can maybe ask ourselves, what is the definition of transfer learning? And we're going to start with this definition to introduce also some notation and some math to be a little bit more tangible in this course, following this definition by Pan and Yang in 2009. And this definition reads out that given a source domain, D source, and learning task T source, a target domain, D target, and learning task T target, transfer learning aims to help improve the learning of the target predictive function, FT, in DT, using the knowledge in the source domain and target, where, and this is the essential part, the source domain and the target domain are not necessarily the same, or respectively, the source task and the target task are not the same. So what we'll need to find out to understand this definition now are these four terms of domain, task, source, and target. And luckily, Pan and Yang have also provided definitions for that, which we can just again read out here just for the purpose of completeness, as it will help us understand the concept a little further and be able to talk about it in a more precise way. So given a specific domain, where the domain here is defined as the pair of some feature space and data distribution P of X and this corresponding feature space in the curly X, a task consists of two components, a label space Y and an objective predictive function Fy, denoted by the pair of these two, which is not observed but can be learned from the training data, which consists of basically data point pairs. Now note that this is a definition for supervised learning, but essentially what this tells us, and these are the important parts that we'll stick to, is that a domain is a pair of data distribution and corresponding feature space, because someone's actually said in the chat that feature space position shift could be a thing. So yes, domain shift would mean that also feature space position can shift. And the task is essentially to find a function. In the supervised case, this is, for example, classification or something similar. But generally, what we can then say, given the definition of the previous slide, that the domain, the source and target domain or task are not the same, is that generally either the source and the target feature space or the source and the target data distribution will change if we say that the domain shifts. And speaking of domain shift, one of the most popular concepts in transfer learning, to get just through the definitions before we encounter some practical examples, is the idea of a very specific form of transfer learning, which has initially been named transductive transfer learning, where the majority of the definition that we see on here is exactly the same as what we've just previously seen, so I'm not going to read it out again. But the quite crucial difference is in the last portion where it says the where it still says that the DS and the DT, so the source and the target domain, are different, but the task remains the same. So people often refer to this as domain adaptation or sometimes as sample selection bias. And what this means is that the task remains the same, but the feature spaces are different, or the feature spaces are the same and the data distribution shifts. And to complete off the definitions, the other half to that would then be called inductive transfer learning, again, where the part to focus on now here is the very last portion, where in addition to this, now we also say the tasks can be different. So the reason why this is called inductive transfer learning is that in the transductive case that we've just had, the domain adaptation case, the intuition may be that the task is not changing. So maybe it's not really necessary to have new data points to find out a good solution for the function. But in the inductive case, if the task itself is actually changing, it may more or less be required to have at least a few, and we can discuss this later, data points that are required to induce a new target predictive function, hence inductive transfer learning. So with the definitions, like the boring parts a little bit out of the way, let's talk about then what you think the central questions could be and what you think the measures of successful transfer learning could be. So we've just, you can again feel free to chat or reply. We've just seen that now the quite crucial part is that we can have shifts from the domain, or we can have shifts in tasks. But if we consider such a shift, what would be a central question and what would be a measure of success for this? Okay, you can start with either or. You can start with maybe giving a central question, or you could start with giving some idea of how you would measure if a transfer, the knowledge transfer is successful. And again, you can feel free to relate this to machine learning, or you can feel free to just give a more general response. Okay, it's also fine. We can just move on and can just move on to the next slide, where I'm just going to talk about this myself then. Anyway, you may have just thought for yourself and just didn't want to voice it, that some of the central questions would be what to transfer, when to transfer, and how to transfer. So it's more or less very intuitive. Sometimes maybe transfer can hurt us, sometimes maybe transfer can help us. And an obvious question would be, what algorithms do we actually use to basically include and do the real transfer parts? Now, for the central objectives, someone has, by the time I've skipped to the slide, actually given an answer, which is a faster learning process and better results in the new tasks, which I have listed as two of the central objectives here. And the third one, just to complement that, would be to reduce the data dependence. So the intuition that the majority of you will have is that if we think of transfer learning and why we want to do transfer learning, it's that first training on the source task and then training on the target task will eventually improve the loss or the measure of accuracy, in contrast to just training on the target task. It is also hypothesized to be faster because you've already built up some knowledge that may be helpful, and respectively, you may reduce the data dependence. So I believe a majority of works would use transfer learning because in the target task or in the target domain, there's less data available than in the source. And so let's then take a look at a couple of transfer learning examples to make this a little bit more tangible of what we've just started talking about. We're going to start with a very simple example, with an old example, where transfer is rather intuitive, I would say. And it's this example of a binary classification task where on the left-hand side of the diagram, you can see the source training data as zeros and ones. And in order to separate the source training data according to two features, you may draw these four hyperplanes that are indicated here. And so if you think about this, let's say 2D example of a binary classification task in terms of transfer, it would be very intuitive to understand which parts need to be transferred and which parts don't need to be transferred. If the only shift in the data, so it's transductive, it's a domain transfer shift, is that the distribution shifts to the right, but the task remains the same. You're still tasked to separate these two classes. As you can then see, what you would basically do if you had a measure, and back then you maybe had this measure to identify what your hyperplanes exactly look like and how they separate the data, you would retain these two hyperplanes that are indicated in this plot that look like this, because they still separate the parts of the data just as before. So if you were to craft an algorithm, and it's not actually mentioned on this slide, that would measure how useful this hyperplane is, then you would vote to keep this. Whereas it's obvious that the two left hyperplanes, they need to move because they don't actually help you at all in figuring out anything about the target training data set. So an old school, in that sense, algorithm to these easy to figure out 2D examples would be to figure out if the hyperplanes you've drawn are still useful, and then just kill the ones that are not, and maybe reinitialize them or reweight them and start learning them again. So in that sense, knowledge in this scenario would be the knowledge of the hyperplanes and the utility. Similarly, if maybe your target and your source domain, you're again in the same scenario where you have these pluses and these minuses here on the left and the source, and then the target, it's these triangles and the green circles, but your task is still binary classification for both of these. What you could also do is, instead of thinking about these hyperplanes, you could go one step further and start thinking about, can you define a transform for both the source and the target into some form of common space where you could again solve this classification task quite easily in this sense. And this is illustrated on this slide, just on a high level, where the idea is that on the left and the right arrow, you both define a transform such that you come into this augmented feature space. And if you think about this, and I suppose that's what the majority of you are going to be familiar with in one way or another, this is more or less the idea that we'll find when we now start talking about deep learning and transfer and deep learning. Why are we going to start talking about deep learning and transfer and deep learning? It's because personally, I believe that this is where transfer learning really took off. So most of the transfer learning that you'll see nowadays will be about deep neural networks and deep learning, transfer learning, because this is where the promise is, this is where the results have been shown. And in order to understand these a little bit further before going into examples, we're going to do a small interlude, a small recap on convolution neural networks. So like I've said in the first lecture, we'll try to keep this course in a way that we don't necessarily go through each and every aspect in complete detail again, but we'll assume that not too much prior knowledge in machine learning is necessary in order to follow the course. So with that, let's dive in what a convolution neural network is and just spend like 3 to 5 minutes on a small recap. The main idea behind convolution neural networks and how people use it is on the very left of this diagram, where we usually have a raw input, and then we have something that we'll refer to as a feature extraction module, and this produces a feature vector, and then we can put something on top. For instance, a trainable classifier module if we want to stick to the classification example. What this looks like in more detail is on the right big diagram of the very popular LINET, where, for example, you could take this handwritten digit as an input, so in this case an image, but it could really be anything, and then you define a convolution on top of it. So a convolution is a weight sharing paradigm, so it has some weights that you slide across the image in this scenario and apply it in order to get a feature map, an activation map. We'll see an example of this on the next slide. And then usually in a deep neural network or a deep convolution neural network, you stack these operations, and sometimes you'll put in some other layers in between, like a pooling layer, which has some different purposes, for example, to reduce the dimensionality or introduce some local invariances, alongside with potentially some operations that are not learnable. Now, if you don't know how training of these things work, don't worry about it. We will very briefly revisit this next week when we talk about not knowledge transfer, but knowledge forgetting, because there we'll figure out how training works and why forgetting is an issue. But for now, to just finish this recap, let's take a look what a convolution does. So a convolution on the left, what we'll assume is that we'll want to eventually achieve multiple learnable patterns. And so here's an example of a pattern that's maybe already learned, illustrated in the center between these two bigger matrices, that has zeros on one side, then 1 in the center and 0 on the other side. So if you think about this as white and black values in an actual image, this would very much look like an edge. And now what you do in a convolution is you take this filter, this pattern, and slide it across the input matrix, the image, at each and every position. So for example, you place it at the position of the red square, or you place it later at the position of the blue square. And what you'll then find is that when you multiply this filter, this convolutional weight matrix, with the input at this respective position, you will either multiply zeros and ones in this scenario, or you'll multiply ones and ones and accumulate into a value that's non-zero. So in the red case, you'll find that the multiplication and the sum will result in a 0. In the blue case, you'll find that the multiplication will result in a 3. And this is because the pattern that you have at this specific position matches the pattern that is found in the image. So if we again assume that this is an edge, 0, 1, 0, so white, black, white, then this matches the edge that's been found at the image at that point. And of course, when we now think of machine learning, then we don't want to impose these patterns up front, so the 0, 1, 0 edge pattern, but we want to learn these patterns automatically through some training mechanisms. And then on the right-hand side, you'll just briefly see how pooling works, which not only reduces the dimensionality, but it can also introduce local invariances. So in this specific example is a 2x2 window of max pooling. So the window works just as the convolutional window. You just put a 2x2 window at each and every position of the input. And in this scenario, you don't apply some complicated weighting scheme, so you don't learn anything at all also, but you just extract the maximum value. So in the red part, you would extract the 20, in the yellow part, you'd extract the 30, and so on. And the reason you want to do this is, apart from dimensionality reduction, this will give you some sort of local invariance with respect to translation in this case, meaning that independently of where the 20 would be positioned within that 2x2 red part, you would still extract the 20 as a value. So in other words, if you have a pattern in the input and you slide it a little bit in the input, this would not result in any change in the output. So that's hence its translation invariant in a very local form. But of course, the intuition is if you stack this into a deep network multiple times, you'll eventually become more invariant. And so if you train these deep neural networks, what you'll end up with potentially on the image task is you'll extract these patterns. You'll extract these convolutional filters that correspond to, like I've just said, for example, edges, as you can see here in this illustration, where you have a lot of these black and white sort of frequency edge filters. And maybe you'll also have some other filters on the bottom, like these color filters, where you have a difference between purple and green, or a difference between orange and blue, and so on. And quite crucially, the key hypothesis in most deep neural networks is that the early layers of deep neural networks, especially convolution neural networks, will learn to extract these very generic patterns. So the features that are extracted are very generic nature, such as these edges and color filters. And the deeper you go into the architecture, the more specific it eventually becomes. And so you can visualize this through several techniques. It's no longer as easy to just as showing these edges when you move to deeper layers, because you've extracted a feature, and then on top of this feature you again compose another pattern, and so it's going to be combinations of pattern, and it's going to be hard to analyze. But people have done these visualization methods where you can, for example, deconvolve, so you can take a specific filter like the one in green here with the star, and you can project it back onto the input and see what precise areas in the image basically get activated when you apply the specific pattern at a specific layer. So in the case of the cat, it looks very much like this is around the nose-eye region. And on the right-hand side, you can see something similar to the the green filter, but with respect to humans, and which humans are the most likely images to correspond, for example, to a high activation for this. And so what does this mean for transfer? That if we assume this hypothesis is true, that the earlier layers of, for example, a deep neural network do in fact extract these very generic features, and the later layers get more specific, like the cat's eyes and nose and so on, then what this means is that transfer learning with deep neural networks maybe could be done by taking these early layers and freezing them and only adapting the higher layers. So transfer learning started then in deep learning, and this is where it took off, like I said, with this idea that we can pre-train a neural network model. It's going to learn these generic features, and then we can use some of them in the less specific layers to transfer to some other task. So one of the earlier interesting experiments in this area was a deep neural network, or deep neural networks trained on the ImageNet dataset, which we had discussed last time. Just as a brief summary, it's an image dataset with more than 1 million images and 1,000 classes. And what the authors of this specific work have investigated is what happens if you split the ImageNet into 2 subsets. So you randomly sample 500 classes for the one set called A, and you'll do the same, or you'll take the remaining classes for the subset B. And what you can then do is you can pre-train the entire neural network model on one of these two subsets. So illustrated here in this green and purple, with these green and purple colors. And what you can then do is investigate what happens when you start locking individual layers and only adapting the upper ones, or when you start maybe pre-initializing these locked layers on the other data set and then continuing to train them. So there are multiple configurations where you can now do this. And the authors have analyzed this in quite detail. And there's some interesting conclusions for this. So the first experiment that you can see here is denoted in the line that's referred to as 2. And the idea here is that we train a neural network on task B, so on this one half of the data set. And then what we do is we freeze the representations of the amount of layers that's indicated on the x-axis, and then start training the rest of the layers when we randomly initialize them again, so random patterns, again on B. So it may not sound very intuitive, but what this is saying is we initialize the early layers with the generic representations on task B, and then try to adapt the later layers with task B again. And maybe perhaps a little bit counterintuitively, what you can see here is that the performance in this procedure actually drops. So what this means is that because a specific part of the network has already initialized here, and the specific part has not already been initialized, the authors have said that this is called fragile co-adaptation because it seems hard to tune only specific parts of an architecture if the remainder is frozen to an already converged solution. So the alternative to this would be maybe a more soft version, which is referred to here as 3, which is the B plus B version, where you do copy the features as well and first test on B and then again on B, but this time the frozen layers that you have will also allow them to adapt a little bit. So in that sense, they're not completely frozen, but they just get transferred, and then you allow them to adapt a little bit. And maybe not so surprisingly, this is the light blue curve that you see here, which is very close to the dashed black line, where essentially the co-adapted interactions that we just talked about before that can harm are now recovered. So you get back to the state that you would expect of just having trained on B itself. So this is maybe something more of a consistency experiment. The natural thing that everyone's interested in, of course, would now be what happens when you do the combination. You train on A and then later you train on B. So it's actually different subsets of different 500 classes. And so again, this experiment has been repeated in both of these versions. In 4, again, in the form that you pre-train on A, and then you lock the early layers or the layers up to 7, and then allow the others to adapt from a random initialized state. Or you do the same version in 5, where you transfer the early stage features, but let them adapt further even in training. And again, maybe not surprisingly, the very hard locking, it only works to a very certain degree. So you can transfer the very early features of layers 1, 2, 3 without much of a performance loss or without much of a change. But if you keep freezing all of the layers on task A and try to use them for task B, your performance will drop because the representations just become increasingly more specific to task A, like we have hypothesized. And conversely, and this is the part where the promise comes from, if you first pre-train on A and you then take this as an initial step as good knowledge for task B and continue tuning on it, you actually have this scenario 5 at the very top with this light red curve that eventually supersedes the black baseline at every single point. So this is what we're interested in, right? This is this transfer that we would like to have. And it's maybe, at least in this picture, it may be very intuitive to reason about the neural networks, although we can already see there are some challenges that are less obvious than maybe initially expected. Now, this has then led to a wave of works, I would say, because you'll find transfer deep learning everywhere nowadays, where this pattern is taken into account and practiced in all its variations. Here again, you can see some of the applications where the source task labels are something like African elephant, wall clock, green snake, and later you transfer to target labels such as person, TV monitor, background, where again, you freeze the convolution layers in this, or you transfer the parameters, you don't freeze them, you transfer the parameters from the early layers, and you add sort of very specific layers at the end that completely adapt to the new task. And I think this is quite cool, because if you look at the source tasks and the target task labels here, then you can see that maybe intuitively they don't have all that much in common. So I mean, a chair and the green snake, they're not really the same thing, right? But because we've hypothesized, and because this seems to empirically be the case, that the lower level abstractions in these convolutional neural networks are of such generic nature, this actually helps us. So this helps us if we want to look at quantitatively, for example, also in situations where the number of labels, the data is scarce. So in this scenario, we can see the dogs and cats on the right-hand side, where one image shows a dog in ImageNet, of which there are a lot. So there are like 150 dog classes in ImageNet, so 100,000 of labeled images of dogs. But the type or the way that an image in ImageNet is captured, it very often has these central objects or central animals in an image, and there's not much sort of clutter around. And maybe there are other data sets like this Pascal VOC on the right-hand side that are more realistic, that feature more realistic also variations of dogs and cats, or dogs and humans, and different scales. But the amount of data that we have here, especially the amount of labeled data, is a lot less. And so in transfer learning here, we can see on this numerical table that there's a difference in whether we just do no pre-training, meaning we just train on Pascal here from scratch, and we do achieve, in fact, decent accuracies here. But when we pre-train, for example, on these 1,000 classes of ImageNet, then this boosts up by quite a significant amount. Like even for the plain class, it's 8%, but for something like BERT, it's close to a 20% gain, which is a lot, and it comes at potentially, let's say, not a free cost, but a very low cost, which is why nowadays, if you look at common frameworks like programming frameworks like PyTorch and TensorFlow, you'll find these model hubs commonly, or these large transformer models that come with pre-initialized weights that you can download that have been pre-trained on some tasks, with the promise that you can now take this and tune this to novel tasks. One specific version of this transfer that has emerged is this idea of few-shot, one-shot, and zero-shot transfer, which I would consider subparts of transfer learning, where the additional idea now is that not only are the representations that we learned similar or useful for various tasks because they're of generic nature, but also that the way that these features map into a feature space has some meaningful properties. And in that sense, for example, if you take two dogs here, you'll find that these two dogs are embedded in 2 points of the feature space that are way closer to another than if you take something like this image of a beach or image of the sea, which may be embedded in a completely different part of the feature space. So to give an example that's maybe less obvious than two dogs, the idea is that you could take, for example, the activations for the fireboat, and you could take the activations for a streetcar, which should share some properties, but others should not be shared. And you can see where they get embedded, and you'll actually really eventually find out that the activations it has for the fireboat and the streetcar partially overlap and partially are distinct. Of course, for the fireboat, you'll see that the parts where there's water and so on, it's not something that you'll have activated in the streetcar, but maybe some of the geometric shapes of what a fireboat and a streetcar look like, they activate together. And so the idea then was that few-shot learning could happen, and few-shot means that we do transfer learning where the number of examples that we have, specifically the number of labeled examples we have in the target, is very low. So really just a few shots in that sense. And the reason we can do that, for example, in one version here, is because we can calculate so-called prototypes of a concept. So prototypes here really trivially just mean we could take something like the mean activation vector, so the mean of the embedding, and then we can use this as the as the anchor to which we calculate distances of wherever something new falls. And then in that sense, we can find out how close a new concept is to the ones we've already seen, and eventually even assign it to that, or eventually fine tune such that we can call it something new, but because we already know sort of which are the most similar concepts in our feature space. And say the even more extreme version of that is one-shot learning, where the idea is really that you just have a single example. And the definition of one-shot learning that I like here is the one that I've put on the slide, where we say that a set of classes is gamma greater than greater than 0, separated with respect to a distance function d if for any pair of examples belonging to the same class, the distance is smaller than the distance between any pair of examples from different classes by at least this gamma. So what this means is we can learn from an extra sample a distance function d that achieves this gamma separation, and then learn a nearest neighbor classifier, where the classifier basically employs this distance function. So it's a way of classification in few-shot / one-shot learning that relies on these embeddings being meaningful and these activations being meaningful, such that you can rely on the distances that you have in this space. An even more extreme version of that, which is often referred to as zero-shot learning, does something quite similar, but it's called zero-shot because it's assumed that no supervised example of the target is available at all. And this is maybe not the most intuitive thing ever, but the rationale behind this is that it's usually considered in applications where you don't just have a single source of information. So often you'll find something like object classes together with attributes in this case, and you have an embedding that aligns both of them together. So you could check, even though if you don't have a label necessarily, maybe you have some attributes, so you could check off the attributes and reason according to that. And to put this a little bit more, maybe in a slightly more algorithmic form or model form without actually having an algorithm here, the common approach would be in general to few-shot, zero-shot, one-shot learning would be this entire idea that you have in either one model or two models that produce some of these embeddings, some of these latent spaces. In this scenario here on the slide, it's a specific form of a machine learning model called the variational autoencoder, where the idea is that in this middle portion, there's a mu and the sigma, so a mean and the standard deviation of a specific distribution, often a Gaussian distribution, that parameterizes these examples. And you'll have this, for example, here for images of a bird and also text or attributes of a bird. And what you'll do is you'll train these together and you'll make sure that the feature space that you have is aligned. In that sense, if you align the feature space, what you could then later do is you could infer one of the modalities from the other. So you could have just the text or just the image, and you could figure out the complementary part. And in that sense, it allows for this few-shot kind of behavior. And quite naively, maybe this aligning of these embeddings could be done just by minimizing distances between the outputs that you initially get. So you could really just, like in this example, put in some measure of maximum mean discrepancy by minimizing the square distance, for example, or using some more elaborate measures like Wasserstein distance and so on. And so all of this, what I've just said, it sounds really promising, right? It sounds like, oh, cool. So maybe initially transfer learning wasn't the most easy thing to do, but now that we know that deep neural networks are so powerful, they have these generic representations, at least in the earlier layers, we can maybe not use them out of the box for anything new, but we can at least use parts of the representations to do like some quick sort of fine tuning, and maybe we also don't need a lot of data for it. So why is this actually challenging? Maybe someone wants to even suggest why this is challenging. Otherwise, I'll again tell you in a second. But I'm already giving you a small spoiler that it is going to be challenging. And so this is going to be a pattern that I'll hope to keep up throughout the course, that I'll tell you about the, let's say, the very positive sides of things, but also tell you about the parts where we maybe need to be a little bit more cautious. Maybe let me give you an example and we can figure out together why it's challenging. So going back, before going into deep neural networks, going back into this very easy example, how would you actually draw hyperplanes to separate this data that I've drawn here? And I'm giving you a small hint. Try 3 because 3 is, I mean, it's going to be hard to do this with 2, so you should draw 3 hyperplanes. But how would you draw 3 hyperplanes to separate this data? Anyone has any suggestions? Okay, I understand this part may be very difficult, very challenging to do in through YouTube because you'll need to write how the hyperplanes, what they should look like. If you're very, yeah, if you're up to the task, you can try doing that. But maybe just let me show you an illustration while you just think for yourself of how you would have done it. But quite crucially, as an example from a very old paper, is that in transfer learning, one of the challenges is that transfer will depend on where you started. Not so surprising, right? But even in this easy example, we can see that we can draw hyperplanes or we can learn parameters in various ways to come up with rather similar, maybe even sort of the same performing solution. So here, even in this example, we could do this. We draw one decision boundary here, and then we have these 2 decision boundaries here. And of course, this is mirrored right now because of my video. Or you could have these this sort of more like triangular style shape decision boundaries and many, many more. And what this then means is that if you think back to this example where I said the data distribution now shifts to the right, and we have to figure out which hyperplanes stay, which hyperplanes do not, then of course the starting point that we have here will majorly influence this decision. In the worst case, none of the hyperplanes are actually useful because we've drawn them in a way that was like too specific to this source data, and so we cannot, or maybe it's very hard to leverage it for new data, and the transformations we would require potentially maybe even exceed what the point where it's beneficial. So it exceeds the point where it's better to just start from scratch in that sense. So there is an idea that unfortunately transfer does not only need to be positive, and we've just seen that a little bit in this one diagram, but there is this idea that transfer can also harm. And when we go to deep neural networks, this specific form of harm versus positive transfer, at least to me, is not very intuitive. So I'm giving you here an example of myself, of my own paper, so that I can only talk about myself here and not necessarily point fingers at others. But some trap that I've fallen into once was that in a paper we've done, we've proposed a data set for concrete defect detection. So you'll see these images on the top left, where the idea is that you figure out what defects are visible in this image. So it could be these exposed bars, it could be a crack that's very hardly visible on the left. And of course you want to solve this task, but again, I mean, this is on infrastructure, it's very hard to assess. You need a drone to fly there to capture the images. It's unlikely that you're going to gather millions of data for this task. So why not use transfer learning? And of course, then at the time, I wasn't so naive to think like, look, I'm going to pre-train on ImageNet and this is somewhat going to transfer, because even I at this time was saying that, I mean, objects and textures, they're quite different, right? So this transfer may not really work that well. But what if I take a different data set, like this materials and context database on the bottom left, that actually, where the task is to separate different materials? Like this comes much closer to what I'm doing here. At least the sort of patterns that I learn, they should be more specific to this task, right? And so we went about transfer learning or trying transfer learning. It's not the main contribution of the paper, but I think it's a good example where we can see, and you can find this in the appendix of the paper, that if we train from scratch here on these 3 specific neural network architectures that were popular a couple of years ago, we can see that unfortunately these values in training from scratch, even though the database is limited in size, is actually much better than if we first transfer either on ImageNet or this material and context database. So in that sense, what we have here is an example where trying to attempt transfer learning really hurts us in the same way that we've observed in this early diagram where we've frozen specific layers, because of all these sort of ideas about co-adaptation, because of also that we're maybe at a point that's harder to start with than just initializing from scratch. But I think the message I want to send here is that at least I was initially expecting that this would be the case for ImageNet, but not necessarily for different data sets that based on textures. And so we always have to ask ourselves then, if we want to attempt transfer learning, how do we actually pick the source task that we use for a target task that we're interested in? How do we pick that respective data set? Because it's not very intuitive to do that. And so my pragmatic maybe response to this is that I believe a lot of the community goes about this in a rather sort of trial and error way, where you just see if it works, right? You just see if tuning to a downstream task actually improves or not, and if it does, you're happy about it. Maybe that's a very that's a too summarized take. Of course, there's some more principal approaches, but looking at blog posts and code examples, this seems to be a little bit of the narrative. Now, you could maybe think of doing this in a slightly more motivated version where you don't only do what we've just talked about before. You don't actually take entire layers. You don't take entire sort of sets of representations to transfer. But maybe what you can do is you can pick a pre-trained model and a target task, and you can try to selectively extract only the parts that are really sort of relevant to the new task. And a measure of relevance in the sense, if we think back of our idea of embeddings and activations, would be, let's extract only the features that actually have high activations. So features where we are maybe more or less sure that they are not completely useless, so they couldn't also harm us. And in fact, this has been in the literature. It has been used in the literature to stick with this example of the materials and context dataset and ImageNet that we've just had. Someone has actually done this where they show that this transfer can indeed be done without harm if we only select the features that activate very well on the new data. But that said, let's get back to this idea of why it's not intuitive of whether we can transfer, whether we cannot transfer, and maybe even harm. And as I said, to me, it's not intuitive why one texture data set is not really working well for the other texture data set. Maybe it's all about the specific idea of extracting only the features that matter, but maybe there are also some other parts that are at least as important and potentially even more important. And so in the next couple of slides, and essentially for the remainder of the lecture, let me tell you a little bit about the issues that to me are extremely non-intuitive that we may face. One of them is illustrated on this slide, which is a specific, admittedly, it's a specific instance where it's not very clear how generic this actually is, but 4 convolution neural networks pre-trained on this ImageNet database, and we recall that ImageNet is so popular because it's been one of the largest databases for a very long time, is that apparently if you train on this, even though there may be some geometric features in the image like this cat, like the shape of the ears and the shape of the paws and so on, that apparently this is much less relevant in the learned patterns than, for example, texture. So what happens, for instance, here is if you take a textured image of elephant skin and you superimpose it or you mix it with this cat image so that the cat texture is kind of a little bit more like elephant skin, it seems that the geometry or the geometric features are largely ignored in the sense of that we'll get a prediction as going to say Indian elephant. And naturally what this then means is that, sure, what we've said is that the features we've extracted are generic, but what we have not made sure about is that the features that we've extracted are also comprehensive in the way that they A, describe all of the data, and B, that there aren't some pitfalls that we're falling into. And so some of these pitfalls I'm going to show you on the next two slides. The first one is maybe a very popular one. The second one maybe less so. But the first one is this idea that there exist these adversarial features. So you may have heard of adversarial features in a different context of attacks. So the idea behind adversarial attacks was that you could take any image or in fact other forms of data inputs and you could perturb only very minor portions of this image, like just change the value a slight bit, but the prediction you would get from the neural network would be completely different. Like it would be very confidently false. And a flip side of this is been shown in an experiment that's quite interesting, is that if you create a data set, which is here called the non-robust data set, that consists only of these perturbations. So you remove basically everything that makes up the image, but only these perturbations that lead to a specific prediction. And you train only on this data set. I mean, you can take a look at it on the bottom, there's not much to discern. You still get a good standard accuracy. And a good standard accuracy here means that you'll get a satisfying accuracy on the original test set here. And so what this means is that this is a very big trap then of all the features having learned something where we're not really clear what this would mean. Like, what would this mean if we do transfer learning on top of this? We've just learned some weird noise patterns that seem to be very specific to certain images. And quite similarly, but maybe more extreme and more worrying, is this idea of confounders. Confounders that luckily have picked up attention a bit in newer literature, but it's something that's still very worrying, where on this example you have the Pascal-Vogt dataset, and what has been discovered is that a lot of the images that have depicted horse have these photography tags at the bottom. And so if you have these photography tags, what the neural network eventually learns is that, oh, look, that's a really easy feature. If this photography tag is present, then my image must contain a horse. And so if you remove this horse tag here, you'll see that there's no region of actual activation, and it's not classified as horse anymore. And of course, this is a very extreme example, but it's something very realistic where confounders in the dataset, and of course for us it's very hard to say what these confounders are if we just randomly acquire images or randomly acquire data from everywhere. Confounders are an issue in deep learning. And maybe one of the potential reasons for this is this idea that at least neural networks seem to have simplicity bias. So in this example, what we see is there are two features on the x and y axis, and the data consists of these blobs, of these blue and red blobs that look like bars. So it's almost like a checkerboard pattern. What the neural network seems to learn is this green boundary. It's this linear green boundary, which is very simple. And surprisingly, this actually only requires one of the two features to arrive at the decision. The much more meaningful way to arrive at the decision would actually be to craft a decision boundary that looks like the orange one, which is more complex, but it actually uses up the entire information that is available to arrive at a good prediction. And so if you think of the introductory lecture, I think I've mentioned this example with apples and oranges, where I believe I said something like, the easiest classifier to craft would be to just differentiate whether it's orange or red. And somehow, at least to some degree, it seems that neural networks fall into this trap and they go towards this pitfall of simplicity, especially if the only task is to discriminate. So then again, the question will be, how useful are the representations actually to transfer? And so we've talked a lot again about neural networks and representational transfer. And let's just sort of circle back to end this lecture on the question of, could we think of other ways to transfer knowledge? Maybe not necessarily other ways in the sense of not using deep learning at all, but even just as complements to the representations that we already have. Are there other ways, additions that we could do that maybe answer some of these questions that we've just discovered? And again, feel free to write whatever you want in the chat, some ideas of how could you improve this? What else could you do? What other forms of knowledge could you include, maybe even in the deep neural network, and so on. Right. While you think about ways to do that, I can give you a suggestion of where I personally think where there exists an interesting direction. And this is not a new direction at all. In fact, it used to be called, among other things, learning from hints. So a hint here is defined as any piece of information about the function. As a matter of fact, an input-output example is a special case of a hint, and a hint may take the form of a global constraint on F, such as a symmetry property or an invariance, and so on. And yes, someone actually has written in the chat that ontologies, graph knowledge, rules, symbols, and so on, I would classify them as precisely fitting to this direction. Maybe not exactly in this definition, but this is the general idea. It's like, what about all the sorts of constraints we have, all the sorts of ideas that we already know about symmetry properties, about invariance, about things that should not be changing. So for those of you not familiar with the word invariance, the idea of invariance is that if you change something in the input, the output remains the same. And to give you a few examples of this, of how symmetries and invariance can be useful independently of whether we're using deep learning or not, and especially for transfer, I'm just going to show this slide here on rotation, for example. If we know that we'll need to figure out various forms of rotation, then of course one machine learning way to do it would be to just gather a very large data set and try to somehow capture all the rotations in this data set, and eventually maybe even augment our data to have different rotations. Because if we do that, we'll assume that our parameters are going to capture this potentially. But maybe an easier way, if we already know this upfront, is to just design our system in a way that this rotation invariance is pre-built in. And so an idea could be that even in a very simple form, could just take the filters and always make sure that whatever pattern we learn always appears in all sorts of rotated variants. So we could put that constraint on the learning. Or similarly, if we think of degrees of scale invariance, for example, so like this is a popular example in vision, because in vision, this is encountered all the time when you have a camera, and of course the image doesn't really care about the actual size of the object. It matters a lot, like what zoom you use, how close you are, all these physical sort of properties that you do not usually provide as metadata to the image. So an idea then is how can we still recognize objects, detect them, classify them, etc., if they continue to appear in images in all sorts of different sizes. And so the naive way would just be to start cropping, to maybe warp them, but then there are all these sorts of distortions and parts that we're cutting out. But a surprisingly simple way to provide maybe not a full solution, but to get a long way, is to do something like on the left, where you construct, for example, a feature pyramid, so a spatial pyramid pooling layer here, where the idea is that independently of the size, at some sort of level of example, a deep neural network or a non-deep neural network, you cut into a specific grid of a predetermined size. So here it's, for example, a 4x4 grid, which results in a fixed length vector, another 2x2 grid, which results in another fixed length vector, and so on. And then you can concatenate this into a fixed length representation. And during the learning process, the parameters will then adapt to sort of which scales should be used depending on what the input looks like. And so it's a maybe a quite easy way to figure this part out. And just to give you a third example, again from one of our papers, but also a very, very old idea, which I'll explain in a second, is what if maybe some of the changes that you have, you already know they're going to appear all the time, independently of what you do. So for example, if you go into this left image of here from our simulator, you know that weather is going to change if you drive around with your car outside, and you know that the light is going to change eventually. So there's going to be parts where where it's very bright. If it's a camera, maybe it's even overexposed. There are parts where it gets dark because it becomes night. And so some of these parts may be very tough to challenge because you have no idea how weather actually manifests itself in images. But the lighting portion, for example, could be rather easy to fix. And so what we've had here was a continual learning procedure where we've continued training while the light has changed. So it became darker and darker. And we've seen that if we do this naively, so we just keep on training, we lose out on a lot of precision here. But we could do something like local binary patterns, LBP here, or photometric color invariance as a pre-processing step, and the results remain surprisingly good. They don't change at all. And so what the key idea here is, for example, that if we know that illumination is an issue in the real world, we could do something like make use of all the ideas that RGB images are very heavily affected by illumination changes. But what is not so much affected, what is actually quasi-invariant, is this idea that color ratios are not. So instead of using an RGB image or RGB video as an input, maybe you could do a small transformation as illustrated on the slide, where we take a specific function like an arctangent and then divide the channels by each other. So for example, for the first channel, we divide the red by the maximum of either green or blue, and then we do the same for the blue divided by the maximum of the red and green. And what we can see, what happens then on the left-hand side, is that the representation we get on the right for the three different channels, this transformed representation, it actually doesn't care so much about the illumination difference in the input. So apart from the very, very top one, where it's overexposed and the ratios no longer are correct, the idea is that if the illumination changes more or less homogeneously, then so do the different channels themselves. So the ratio itself is not too much affected by that. So the representation we get here discounts the lighting changes. And alternatively, we could do this with maybe even better with so-called local binary patterns, which is another very popular approach from the traditional computer vision literature, where the idea is here to take any pixel or any value in the data point and then start looking at all the neighboring pixels. And depending on whether the pixel is greater than the value we're considering or smaller, we'll give it a 0 or 1. And then we can just figure out the histogram over those values and create a new feature from that. And again, the idea is that even if we shine a flashlight at something, then within the small region of neighbors, the absolute ranking between the pixels is not going to be changed. So something that was brighter before is now again going to be brighter still. And so it's quite interesting because it's a different form, maybe not of knowledge transfer, but a different approach to transfer learning or domain adaptation, in the sense that some of the parts of our problem, maybe we don't need representations or parameters to transfer because we already know the types of changes that we're going to expect. And of course, here, the thing I'm going to say is that both extremes maybe are hard to do. So going the full route of trying to tackle everything by modeling it in this way maybe is not realistically achievable in the entirety of the world. And maybe just learning parameters is also not the best thing to do. But potentially a combination of both of these ideas, like embed the knowledge where we can and learn the parameters everywhere else, is a good idea. So if you've been following the recent discussions on like neurosymbolic versus deep learning and so on, from my perspective, it's not really a versus, it's more like a together without delving too much into these political details. And so to finish up this lecture today, we've talked, as a summary, we've talked about knowledge transfer. We've mainly talked about the idea how knowledge transfers in the positive direction, so how we can improve or how we can figure out which parts to retain to improve. We've not talked so much about the fact that what happens when we also now not only go with this early definition of does the n+1 task sort of gain from having learned the n task before. So do we help the new task with the knowledge we already have? But we haven't looked at the part where we care also about whether the end tasks, so the tasks that we've had before, are both retained or maybe even improved retrospectively. So this is something that we'll go into the next week, where we, instead of looking at knowledge transfer in the positive direction, we'll look at knowledge retention, or phrase the other way around. How can we do this knowledge transfer without forgetting what we've already learned? And to end on a more full-fledged definition of lifelong learning, because we started the lecture with that today, and it was maybe not the most satisfying definition of lifelong learning. I wanted to put up this more recent version of the definition for lifelong learning, which you can feel free to read. I'm not going to read it out in detail here. A lot of the ideas are still the same as before. The additions here are mainly that of a knowledge base, more specifically, and the part that I've marked in orange here, which reads out that it can optimize any task by treating the rest of the tasks as previous tasks, and the knowledge base maintains the knowledge learned and accumulated from learning the previous tasks. Because whatever we've looked at today, the primary objective and the only thing we cared about is, if we've trained on a source, are these representations useful for a target? Can we improve the target? Can we learn faster on the target? Can we use less data on the target? But we've never really cared so far yet about the fact that what happens to our source task when we do that? What happens to the initial solution of our source? And as a small sort of teaser for the next week, unfortunately, knowledge retention, especially in machine learning models where we put knowledge synonymous with parameters, is quite challenging. So it's a challenge that's persisted for a long time, and it's still largely not solved. But we're going to look at how this challenge comes about, why these machine learning models forget, and maybe start talking about ways to alleviate forgetting. And with that, today's lecture is at an end. Feel free to, again, as always, ask questions, write something in the chat, write an email later, and so on. I'm going to stay on YouTube for another 2 minutes if you want to do so. And after that, I'll end the stream. Thanks for joining. Thanks for your attention. Thanks for the participation. For those of you who have participated in voice or chat, appreciate it. Okay, if there are no more questions on YouTube, I appreciate the thank you note from your side. I will end the stream, and looking forward to seeing you next time when we talk about forgetting.